So, how many of you, however, looked into the night sky? I mean, like, just show me your hands. Show me some hands, right? I mean, gazed, right? I mean, it's beautiful. There's stars, planets. I mean, anything you want to see, you'll envision it because of how beautiful the night sky is. Well, when we look into this field of celestial bodies, we see something far more important than ourselves. We see our past. Light coming from multiple different distances away, showing us and shedding important information on us about what life used to be like, way back when dinosaurs, way back in the Cretaceous periods, and many different periods of the past. Well, all these celestial bodies we observe follow certain rules, rules physicists and philosophers have come up with over multiple years. Right. Yeah. Now, these rules, whether we say they be defined entirely by physics or defined by philosophy, are very crucial for us to understand our world and our universe. So, physics. It's a word we encounter, right, in elementary school and in high school. Big mathematical equations, difficult things to solve. I mean, it's quite difficult. But physics, in reality, is the study of motion, the study of multiple different aspects of how we observe matter, of how we observe its movement, of how we observe its position anywhere at any time. A few different aspects of physics. We can observe it at multiple different levels, whether it be the smallest elements of matter, the atom, involved with it an electron probability density field. Where do we even know where that electron is? We can't ever predict it, but we can tell you where it might be. Space-time diagrams and how the curvature of our space is oriented. How the Earth fits into a gap in space where we can say, this is how we can diagram our world. And even as simple as a moving car, something we observe on our highways and our roads, involves an aspect of motion, something which moves, something which has energy, force, big words that are associated with this whole thing of physics. Philosophy. Philosophy is the systematic study of critical questions which shed insight on things like knowledge, reality, evolution, and very important topics in order to understand our existence and what is important to us. Discussing the intersection between philosophy and physics is key, because where physics can't explain things, we use our minds to come up with incredible solutions, to generate mind-boggling, sometimes completely irresponsible solutions to the problems physics poses. Three physicists who have both been involved in the field of both physics and philosophy are René Descartes, Albert Einstein, and Galileo Galilei. René Descartes, famous for his work in wave phenomena, he argued that the intersection between nature and the mind is equally as important as in any physics topic we study. Why? Because it sheds light on our existence, where we came from. Albert Einstein, famous for his work in relativity and whatnot to do with the atom, argued that if the universe is technically comprehensible, then we should be able to understand, and it shows that he understands and has a deep appreciation for how our universe is composed. Galileo Galilei, although silenced by the church for condemning its physics knowledge. I mean, he was right on that the Earth revolves around the sun, but the church did not agree with his laws on planetary motion. He argued that nature, similar to Descartes, that nature plays a very important role in our understanding of existence, of evolution, and everything associated with the human body. Now, this is where it gets a bit more tricky. Discussing the terms explainable versus unexplainable. How do we quantify something to be explainable? Well, we make observations. We take experiments. As physicists, we trial as many pieces of data as we can, and we approach a trend, whether that be graphically or whether that be mentally. Good example, and I mean, of course, we have people who contradict it. Evolution. We can study fossils to see certain patterns in the evolution of bones, from our ancestors to now. Looking at all these three diagrams, we see us at the end. But we see a chimpanzee, a gibbon, a gorilla. All animals we observe in nature today who display similar behavioral traits as do us. Darwin, when he visited the islands of Galapagos and observed the patterns in finches and came up with his whole theories on the idea of natural selection, approached similar strategies to figure out what could quantify us. What can make us explainable? How do we exist here today if the Earth at one point was this hot planet where no life could have thrived? But then we move to the unexplainable, the atom. Well, if we look at this box right here, and we try to zoom in on it, right? Well, classical physics tells us we should see bunches of small particles. Well, if you were to even take the best microscopes, the best electron microscopes in the world and zoom in on that box, you'd still see black. Why? The atom was proposed by physicists to explain the reactions that occur in nature logically, without the need for any method of contradiction. The atom, we can't see it, but we can see it being used. Nuclear fission. How do we gain energy from nuclear reactions? It's an example of splitting the atom. So, although, this very detailed photo of an atom up here, of course, it does not show us what is truly explainable. It gives us a hint into what is not explainable. So, when physics leaves, when we can no longer give a mathematical definition to every aspect of life, we enter philosophy. Now, these two are also physicists. They're both physicists and philosophers, Niels Bohr and Werner Heisenberg. Heisenberg is famous for his work on his very well-known uncertainty principle, which shows that you can never determine the exact position and speed of a subatomic particle. Even though we have all this string theory, all the velocimetry out there in the world with multiple pieces of technology to help us gain evidence into it, we can never know. Niels Bohr, Nobel Prize-winning physicist, he once said that the opposite of an incorrect statement is a correct statement, but the opposite of a profound truth could very well be another profound truth. Now, what does this exactly mean? I'm going to touch later on something called, it's about the observer principle. Niels Bohr is implying that no matter what happens, the opposite of an incorrect statement could be a correct statement. Well, yeah, apples are, blue. Well, we see apples are red, so yeah, in that specific case, it's a wrong statement. But in a certain way, not every correct thing not every profound truth has an entire opposite. Let me explain why. Here. Seems as if, yeah, there we go. So, fortunately, it seems left out a slide, but doesn't matter, I'll explain it quickly. So, we have, I'm going to explain a certain principle here that we're going to discuss. It's about the observer principle. So, imagine I'm pumping air into a bike here, okay? We have a few wheels here, and I'm trying to put air into it. I want to determine the amount of pressure inside that wheel. Well, I can look at it, and then I take my pressure, right, and then I try and psst. That time in which I've taken out the pin and put another one in, there's a little bit of pressure that's gone out. So that value that I'm reading right here in some level of PSI is not what I wanted to find. I wanted to find the initial PSI of when I said, I want to find the pressure inside that tire. Me being involved in part of the experimentation to that experiment has ruined the results. Now let's put this into an experiment that was done with quantum physics. Scientists use something called the double slit experiment, where you have two slits, if you can try and imagine it, you have a little line here and then two above it. They tried to determine the nature of an electron, whether it being a wave or whether it being a particle. Now when you put tons of electrons through these double slits, and you put a detector, so something that can look at the graphical display on what is being left over from the traces of whether it be a particle or a wave, it showed the electron acting as a particle. So yay, the electron's a particle, right? That's it. There's no other nature to it. Unfortunately, not so. When scientists, notably physicist Stanford, removed that detector, it was no longer a localized space-time event. The electrons, after they passed through that double slit, spread out over all of space and time, symbolizing that it was a wave. Now, how can something as an electron be both a particle and a wave, yet we can never observe it at the same time? It blows my mind that we cannot gain an understanding into something that we observe with our own eyes, but when we turn the detector off, it's completely different. This is where philosophy enters and helps us try to gain some explanation as to what's going on. Well, I'm going to revisit this slide because Niels Bohr's statement is now what I'm going to restate. The opposite of a correct statement may be an incorrect statement, is an incorrect statement. But the opposite of a profound truth may very well be another profound truth. So, if we're going to discuss this idea of the profound truth about the electron being a particle and a wave, classical physics denies that. Classical physics states multiple incorrect things, but one being that the electron is a particle, right? It orbits around a nucleus in an atom. Well, we just witnessed, Stanford scientists witnessed that it was both a particle and a wave. So how can we say that one is wrong when we've observed both? I mean, could our entire experiment have been done wrong? Probably not. So what we say is that they're both equally important and trying to help us gain more insight into what our universe is. Back to Werner Heisenberg. Developing on this, he said, the universe is more complex than we think, but it is also more complex than we can think. Even though we can develop experiments that can test what happens far out in space, what happens deep down in the tiniest elements of that box, we can never determine what has actually happened. But we can gain insight into it through multiple processes of experimentation and development of philosophical thoughts. Well, a life with just physics and no philosophy is quite boring. We'd be restrained to mathematical restraints and unable to express our philosophical ideas, the ideas which allow us to be creative and expand beyond what is just general maths. A world with just philosophy and no physics? Well, we wouldn't have mathematical ideas. We wouldn't know what simple formulas were, and we wouldn't have a purpose to school because you weren't learning critical thinking through the understanding of physics and sciences. So, we need both because it's quite evident that physics and philosophy are the two sides of a coin. The coins we use to purchase tickets to the theater of the universe itself. Thank you.